Okay, so let's start. I hope you enjoyed the lectures last week when I was away. So let's move on. So basically, this is the last sort of chapter in the discriminative, if you want, part of the class. Next, either Wednesday or next week, we're going to move to talk about Bayesian methods. So before we start here, just a summary of what happened the last couple of weeks. So midterm exams, I assume you've all seen it on oh, what's this? Just a second. Ooh. One second. Mistake here. Okay. Okay. Yeah, that's better. That's this year. So overall, actually, from my perspective, it looks pretty good. So here is how it looks. So this is a graph of that shows 419, which is the majority of the class, and 519, which is the majority of the class in green, and 419 in blue. Overall, it looks like this. Which is, as I said, from my perspective, a pretty good histogram. So, as I said, also on Piazza, the class is graded. So basically, this is kind of the median, and this should be about B+. So if you did 60 and above, or a lot above 60, you're okay. If you did less than that, should work harder or figure out what you did wrong. Either way, solutions are available or will be available any time now. So go over it and try to understand. Ask questions in the office hours and the recitations. Okay, questions? No questions. Okay, so a couple more comments, projects. So you all got short comments. I do want to talk with all the project teams, so please come to the office hours. I'm not going to organize it because I assume your schedule is random enough that it will be organized. I will have longer office hours in the next 2 weeks, Monday and Tuesday. So please come, please prepare a short 3-minute spiel of what your project is about so we can have short meetings that will be useful. That's basically it. Any questions, comments, suggestions? No. Okay, so let's move on then. So where are we? I mean, this is a slide that you've seen already. We talked a lot about algorithms. We talked a little bit about theory. And we have a notion of learnability that we understand. So basically, we know something about generalization. We can say something about how will the algorithm do on the next example it sees. And we know how it depends, or what it depends on, specifically on the expressiveness of the hypothesis space you're using. And what we started to talk about last time, and we'll continue today about, is really about algorithmic implications of the theory. So we talked about support vector machines, which is a very powerful learning algorithm that was really triggered by understanding the theory of learning. And today we're going to talk about another algorithm that really has the same kind of properties. And this is an approach that is called boosting. So boosting today is really a general learning paradigms for putting together a strong learner given a collection of weak learners. And strong and weak, as you will see in a second, are actually technical terms. And it doesn't matter what learners you use. It's basically general paradigms, whatever the weak learners are. They could be decision trees, that could be linear functions, they could be neural networks, and you can use them under the boosting paradigm. So the original boosting algorithm was really proposed as an answer to a theoretical question, which I'll pose in a second, in a paper from '89, which is now, what, 30 years ago. A very, very good paper still. I really suggest looking at it. The Strength of Weak Learnability by Rob Shapiri. And really, this theory resulted in a lot of very interesting results and kind of deeper understanding of learning beyond just this algorithm. I'm not going to go into these details. You can read it and look at the original paper if you're interested. But it has, beyond the theory, it actually had really huge practical impact. Now, today, people think about it as one member in a family of ensemble algorithms, and we're going to talk about a few other ensemble algorithms, but this one has stronger guarantees than others. You can also play with a demo. I'm going to give an example, talk a little bit about the theory of boosting, and the reason I'm going to talk about it is because it's actually gives some insights, and from your perspective, some understanding of what does it mean to quantify error, and so on. Okay, so this is the one way to think about the motivation. This is an example that is taken from the 90s, from AT&T, that used to be the main phone company, and they tried to develop a system that was called How May I Help You? So someone would call, ask a question about what to do. Some of these terms here are ancient, but companies are still trying to build systems that will help you, and still we don't know how to do this well. So this is actually current. So the idea was that you ask a question, and this system automatically categorizes your call to a type of call and navigates you to someone that can help you or can help you automatically. So the observation they made is that it's very difficult to take a comment or questions that someone gives and understand what it says and navigate it properly. But it's relatively easy to find some rule of thumbs, based on keywords in the input. And so if the word card was mentioned, they will navigate it to someone that deals with calling cards, and so on. So this part was easy. So the question was, can we do something with this simple rule of thumbs that are relatively precise, but of course have very low recall because they address only a small percentage of the calls. And this is where they tried to use the boosting approach that was basically try to use an existing algorithm that was developed earlier. And the idea was this. Select a small number of examples, small subset of examples, derive a rule of thumb for this set of examples, take another set of examples, derive a rule of thumb for that, repeat this until you get good enough coverage, and combine the learned rules into a single hypothesis. Now, of course, this brings up two questions: how to choose the subsets of examples, and how to put them together. How to put the new simple, the collection of rule of thumbs into one hypothesis. And boosting is a general method for doing this, converting a set of rule of thumbs into a highly accurate prediction rule. Okay, so really, as I said, this started with a theoretical motivation that also has a pen angle to it, which you'll see in a second. So you all know about PEC algorithm, which today I'm going to call the strong PEC algorithm. And that says that for any distribution, for any positive epsilon and delta, if you see enough random examples, a strong PEC algorithm can find a hypothesis with error less than epsilon, with high confidence, at least 1 minus delta. That's what it means. So, and the key issue is that basically you can find a hypothesis with as small an error as you want. You can choose your epsilon, and the number of examples will just have to go up as your epsilon, as your desired epsilon goes down. Weak PEC algorithm is the same, only that it holds for some epsilon that is bounded away from a half. So a weak PEC algorithm only guarantees that we can make, that we can do better than chance, right? So we're talking about binary classification, yes or no, positive or negative, and I want that my error is going to be bounded away from a half, 3/8, a quarter, something that is below a half. But that's it, not for every small epsilon. So now the question is, let's assume, yes?
Does this apply only to binary classifiers?
So the way I'm defining it here, it applies for binary. This can be extended also for multi-class, yes?
How is that different? Can you just make the right-hand side as small as you want it?
What is the right-hand side here?
1/2 minus not quite 1.
No, so this is a fixed number. This gamma is a fixed number.
Determined by what?
Determined by the world, whatever my algorithm can do. So all my requirement is that I can do, I can learn with epsilon that is a little bit less than a half. That's it. And the a little bit is defined by this gamma. It could be 1/100th, or 1/8, or 1/50, whatever it is. But that's my requirement. Now notice that in the strong PEC algorithm, you choose your epsilon, and the algorithm should do it for every epsilon. Here, it's not the case. It should do it for some epsilon that is below a half. That's it.
Okay.
So that's the key difference. Now the question arises, let's assume I give you a box that has a weak PEC learning algorithm. It can always learn with error less than a quarter. Can you make it somehow, can you use this box and make it a PEC learning algorithm? Can you use it such that for every epsilon that you give me, I can use this box many times perhaps, and derive an algorithm that has as small an error as you want? So this was a problem that was posed by Les Valiant and Michael Kearns. This was kind of one of the final steps in Michael Kearns' PhD thesis. Does weak learnability imply strong learnability? That's the question, right? So I give you an algorithm that can always predict with error a quarter. Can you make it a PEC learning algorithm? And in fact, and this is actually a very interesting point that I already mentioned before, it shows the power, or this argument shows the importance of distribution-free assumption, because what they were able to show in 88 is that it's not true if you're learning only over the uniform distribution. That is, if it so happened that you have a weak pack learning algorithm over the uniform distribution, it does not mean that you also have a strong pack learning algorithm over the uniform distribution. So this was a negative result. But you already know that we actually need the uniform, the distribution-free assumption, because we gave a few other examples where if you just know how to learn over a single distribution, you cannot transform the distribution, you cannot blow up the feature space, because this changes the distribution. So perhaps it's natural that a negative result over the uniform distribution doesn't necessarily mean a negative result in general. And indeed, the next step was Rob Shapiri's PhD thesis in '89 that showed the strength of weak learnability. Basically, he showed that he can take a weak learner, he can call it 3 times on 3 modified distributions, and this was key. You cannot fix the distribution. You have to be able to do it on different distributions. And then he was able to get a boost in the accuracy, which means the epsilon went down. And then you can apply this recursively and get whatever epsilon you want. So the history really here is really interesting. So this was the first boosting algorithm. A year later, Yoav Freund gave a different boosting algorithm that was called boost by majority. In '92, this is where the AT&T group tried to actually use boosting over this example that I showed before. How may I help you? And it didn't really work. I mean, there were a few practical drawbacks. They couldn't get it to work. A few years later, Freund and Shapiro introduced a new algorithm that is called AdaBoost for adaptive boosting, which is a variation of the 2 previous boosting algorithms that were presented. And this was shown to have strong practical advantages over previous boosting algorithm, and the rest is history. So since then, basically thousands of papers were written on AdaBoost, a lot of applications. In many respects, this is one of the strongest learning algorithms there is today over various things. I mean, you can put it over decision trees, you can put it over neural networks. It's basically very, very commonly used as a very strong approach to learning. So I just want to point out that there are some interesting lessons here also for PhD students, multiple lessons. One is, you can see that the problem was solved in principle in '89 with Rob Shapiri's thesis, but this wasn't the end of it. So if someone writes a paper about a problem, it doesn't mean that it's done, you should do something else. You can still work on this problem and get better solutions or other solutions that will provide insights and probably advance the field. That's one lesson. Lesson 2 is, in '95, when Freund and Shapiro tried to publish the AdaBoost algorithm, their paper was rejected multiple times from conferences because people told them, well, there's already a boosting algorithm. You don't add, it's not novel enough. And eventually they managed to publish it in a kind of 3rd-rate conference. And this is very, very highly cited paper and had a huge impact. So again, if a reviewer tells you that your work isn't good enough and you believe in what you're doing, you should keep going. Something like AdaBoost could come out of it. Okay, so now that we know the history, let's go to the technical side. So what is boosting? So we'll be starting with a training set. We have M examples, M labeled examples. Yi is plus or minus 1. And the algorithm goes by T, capital T rounds. We construct a distribution over the examples. So basically, we have a fixed set of examples. Constructing a distribution means that we put weights on the examples. The sum of the weights is going to be 1. But this will dictate how we measure error, right? Because typically, when we just look at the examples, the error is the number of examples we get wrong. But if different examples have different weights, it's not the number, but rather the total weight of the examples that we get wrong. So this distribution is important. We're going to find a weak hypothesis, what I called before a rule of thumb, which we call HT, with small error, epsilon t. And this is, again, where the distribution comes in. Epsilon t is the probability that HT of xy is different than yi on the current distribution. And then we're going to output, and after we run these t times, we're going to output a final hypothesis that will take all the earlier hypotheses into account. So in order to give you details, I need to talk about the distribution. We need to talk about what is the weak hypothesis and how to account for it, and we need to talk about the final hypothesis. Questions so far? Okay. So how do we construct the distribution? We're going to start with the uniform distribution. So we have M examples. D1 of I is going to be 1 over M. And then we're going to change the distribution, and we're going to define dt plus 1 to be dt divided by zt, some constant that we're going to define soon, times e to the minus alpha t, or times e to the plus alpha t. Again, alpha t is a constant that we're going to define in a second. If we are making a mistake, if y is different than ht, we're going to multiply the previous distribution by e to the alpha t. If we got it right, we're going to multiply it by e to the minus alpha t. And basically, all I'm saying here is that we can just write this in one formula, and you're familiar with this already. This is basically dt of I divided by this constant z of t times e to the minus alpha t times this. Now, you know already that if this is positive, it means that we got it right, the product yi times h. If this is negative, it means that we got it wrong, and therefore you get these two rules combined into this. Okay, so as I said, zt is some normalization constant because we want dt plus 1 to be a distribution. And alpha t is a constant that is a function of epsilon. So now this is a little bit loaded, this slide, so let's try to understand what it means. So the first thing, okay, before that, the final hypothesis is going to be the weighted sum of the hypotheses where ht has weight alpha t. Okay, so basically we are learning a linear hypothesis, very similar to what you've done already in homework 1, only that we learn the HTs, or we combine the HTs in a specific way with these alpha t's that are determined incrementally. Okay, so let's first of all, what is this alpha t? What can you say about alpha t? So the first point I want to make is that the weak learning assumption means that this alpha t is a positive number. Why is that? So let's just focus on this alpha t. So what do you know about epsilon t? It's less than a half. So 1 minus epsilon t is greater than a half. This is less than a half, so this ratio here is greater than 1, and therefore ln of this is positive. Okay? So due to the assumption, we get that alpha t is positive. I'm writing it here again. So, and therefore, because alpha t is positive, e to the alpha t is going to be greater than 1. E to the minus alpha t is going to be less than 1, which means that when I do not make a mistake, I'm multiplying the previous weight by something that is smaller than 1. I'm demoting the weight. If I did make a mistake, the second line here, I'm multiplying the previous weight by a number that is greater than 1. So I'm increasing the weight. So essentially, we take an example. If we made a mistake on it, we are increasing its weight because we basically want to focus on this example more. It's going to carry more weight now. So the next round, we're going to focus on it. We're going to have to focus on it more if we want to maintain our error. And if we did not make a mistake on it, we reduce its error. It's less important. We already know how to deal with this example. Basically, this is what the algorithm is doing. What is this ZT? This ZT is just a normalization factor, right? So I want to make sure that the sum of all this over all the m examples is 1. So basically, this is defined as the sum of all examples, dt e to the minus this, right? And now when I divide by zt, I get 1. Okay, so that's the algorithm. Now you can imagine taking this, I'm defining it here as dt plus 1. dt plus 1 is dt times something divided by zt. Now you can imagine writing this recursively, go all the way down to d1 of I, which is 1 over m. So basically it means that every time you'll multiply it by this e to the power of something and divide by the appropriate zt, so you'll get this consecutive multiplication of exponents. Yeah?
What is the capital D in this case again?
A distribution. dt is a distribution over the examples. And I'm starting with uniform distribution, so dt of the ith example is 1 over m, and then I'm defining how it's going to behave as I progress with my algorithm. Yeah?
Does this mean you take m examples and then you give more weightage to some examples and less weightage to
Right. We'll see an example in a second. Yeah?
What is the summation for 0 t? Is that from 1 to t or 1 to m?
It's I is the examples, is the index into the examples. So it's over m examples.
For all zt's, it's the summations from...
Now, the summation is over I here, and I is the index into the example. Right? So dt of I here, I have examples, I have m examples. So the distribution is over m examples. I started with each example weighs 1 over m, and I'm changing this. So let's look at this example. So I'm starting here with 10 examples, 5 positive, 5 negative. This is my D1. All the pluses and minuses have the same, all the examples here have the same size, which means I'm thinking about it as a uniform distribution. My first hypothesis is going to be this vertical line that I call here H1, where to the left of the vertical line, I'm saying positive. To the right of the vertical line, I'm saying negative. Okay, so this is the top box here. What you can see is that I made 3 mistakes, right? These circled pluses. These are pluses that are in the negative region. I made a mistake on them. So my epsilon 1 is 0.3. 3 out of the 10 are mistakes. And the distribution is uniform. Each example weighs 0.1. And if you do the math, you will see that if epsilon is 0.3, it means that alpha 1 is going to be 0.42. So now I'm changing the distribution. How do I change the distribution? I'm multiplying everything but by e to the alpha. So for these three examples, basically I'm making them larger. These pluses become larger because I made mistakes on them. All the rest are going to be multiplied by a number that is smaller than 1. They become smaller. Again, the sum of the weights of all these, the distribution of all these, has to be 1. So once 3 of them become larger, the other 7 have to become smaller. That's the first round. So my second hypothesis, H2, is another vertical line, where to the right of it I'm going to say negative, and to the left of it I'm going to say positive. Again, you can see that I made 3 mistakes. These 3 negatives are in the positive region. These are the circled negatives. And again, I made 3 mistakes out of 10. But now epsilon 2 is 0.21. And the reason is that these 3 circled examples weigh less now because I shrink their size in the previous round. So now epsilon is 0.21. Notice that, and if you do the math, you will see that alpha 2 is going to be larger than before, 0.65. Makes a lot of sense, right? So we know that alpha is going to grow where epsilon goes down, which intuitively says if your hypothesis is better, which means its error is smaller, it's the weight of the hypothesis, the alpha, is going to go up. I want to take into account stronger hypotheses more than weaker hypotheses. Right? Yes?
But so the epsilon is smaller for a particular distribution, but we want to talk about global guarantees, right? So it doesn't exactly, it's not exactly very simply intuitive that the smaller the epsilon, the more weight you want to give it, because the epsilon was small because of a particular distribution you gave.
Yeah. So maybe it's not intuitive to you. We'll see that this is actually the right thing to do. But at this point, I want you to understand the technology. Basically, we started with uniform distribution. We changed the distribution, which means the epsilon changed. Even if it's the same number of mistakes, the error is not defined by the number of mistakes, but rather the weight of the mistakes, and therefore it went down. So now I changed, now my D3 arrives, and again, what I did is these 3 became larger. These are the 3 minuses here. All the rest became smaller. So these big pluses here became a little bit smaller, and these examples on which I always was right are even smaller now. H3 is this horizontal line that says plus above it. Again, I have 3 mistakes, 1 negative in this case and 2 positives. And again, epsilon 3, even though it's 3 mistakes, is even smaller, it's 0.14. And if you compute it, alpha 3 is going to be 0.92. And that's going to be enough. So my final hypothesis is going to be the linear sum of these 3 hypotheses, 0.42 times the first one, 0.65 the second, 0.92 the third, and it's going to look like this. So below, to the right of this line, I'm going to say negative. To the left of this line, I'm going to say negative. Above this line, I'm going to say positive. And you can see that this final hypothesis is perfect, makes no mistakes on this hypothesis. Okay, so it works. We're going to try to argue it a little bit better, but one interesting thing about the final hypothesis is that it's possible that you already make here no mistakes with the combined hypothesis, but you can still learn. I mean, I can still add H4, H5, H6, and so on. Each one of these H's could still make mistakes. and if I add them to my final hypothesis, boosting will still learn. And its generalization ability is going to improve. Yes? Maybe it looks like in this example, but it's a good question. So in fact, it turns out that boosting is very robust to overfitting. So in fact, for years, people thought that boosting never overfits. It turns out that once you get to like 10,000 hypotheses or something like this, you can get it to overfit. But boosting is relatively reliable in this sense and doesn't overfit. Of course, this is a toy example, so maybe the lines are too close to the examples here. Okay, so why does it work? So I want to say something. I'm not going to give all the analysis. All the analysis is here, but I want to point out a few things. Yes?
So when do we know like when to stop? Like you said, okay, I'm going to stop after 3 different hypotheses. Like how do you
We'll say something about this. But basically, it's just like any other learning algorithm. You have to decide on your stopping criteria when, in this case, when t, the number of rounds, is large enough, or when the error is small enough on the development set. Basically, that's the idea.
No, are you creating the hypotheses?
Okay, so I said nothing about H's, how to create the H's. So that's your own job. So you can invent the weak hypothesis any way you want, but they have to satisfy the assumptions, and the assumption is that they are weak hypotheses. And by weak hypothesis, we mean that they are guaranteed to have error bounded away from a half on any distribution that I'm going to give you. So that's a very important assumption. So let's just see what does the theorem say. So the theorem says run AdaBoost. Let's assume that epsilon t is bounded away from a half, so it's a half minus some positive number, and this gamma t doesn't have to be fixed. It could be a function of t also. So in the first round, you have it a quarter, and then you have it an eighth, and so on. Then the training error is going to be, we're going to look at this a little bit later, but basically, the training error of the final hypothesis is going to be less than e to the minus 2 times sum of all the gamma t's squared. Let's just say something about this. So if I'm choosing gamma that is smaller than all the gamma t's, which I can always do, right? All of them are positive numbers. I have t rounds. T is, say, 101. So I can take a number that is smaller than all these 101 numbers. I'm going to call it gamma. So it means that the training error is less than e to the minus 2 gamma squared times t, capital T. And that's the theorem. Now notice that that's why it's called AdaBoost, because it's adaptive. It doesn't need to know what is gamma. It doesn't need to know what's t a priori. It has this guarantee because this gamma always exists. So the first question is, what does that mean? What does this training error less than this means to us? What's your interpretation of this? Good, bad? Yeah?
I don't know if this is what you're going for here, but since less than 1, it's going to converge to as small as we want.
As small as we want. So as t goes up, because gamma is a positive number, the training error is going to be as small as we want. Okay? So that's an important, so that's the property of AdaBoost. If you give it H's, weak hypothesis, you can get the training error of the final hypothesis to be as small as you want. Now, of course, you have to ask yourself, why do we state the theorem in terms of minimizing training error? That's not what we want, right? So we already answered 2. We said that the bound means that the training error of the final hypothesis can be as small as we want, as a function of t, capital T. Yes?
Is it because you said, as you said, it's quite robust, so due to overfitting, so if you reduce training error, normally the risk of that is overfitting too much, but then if you don't have
Okay, but that's true, but that's because I promised it to you, but I didn't show it. But you can answer 1 given what you've already seen in the class.
We can reduce training error, we can reduce the upper bound for the whole distribution.
So that's what we've shown, right? So basically the role of the learning theory part of the class was basically to tell you 1 is enough here, right? So all you need, if you are working with a small hypothesis space, in this case, it's a linear function over the h's. If you're working with a bounded small hypothesis space, all you care about is the training error. It's going to be okay in the future, right? This is what the Peck theorem says. And therefore, it's enough for us to state the theorem in terms of training error, and we know it's going to be okay. Okay, so the other thing is, what does that mean? So we talked about this part, right? So this part directly can be written this way, which basically means the training error can go as low as you want. Really what we need is to prove this one, because the rest, from here to here, there's just simple algebra, which I'm writing here, and you can go over it. Basically, I'm writing this epsilon t. So this says that the training error is less than the product over all t's of this expression. Epsilon t, 1 minus epsilon t square root of times 2. And here I'm just writing it. This is just simple algebra. And the second part is an inequality that we've already seen when we talked about Peck learning. So e to the minus 2 gamma square is greater than 1 minus 2 gamma square. Okay, so basically that's what we want to prove. I'm not going to go into the details of the proof completely, but I want to show a few highlights that are important because it really gives insight into what's happening here. So the first one is basically unwrapping the recursion. So I want to write an expression for the final distribution of an example I. The intuition that you want to have here is that I'm starting with uniform, and at the end, those examples that I made a lot of mistakes on are going to have high weight, because I really want my weak hypothesis to focus on them and get them right. If an example has a very high weight, the weak hypothesis will have to get it right so that its error is less than a half, right? So I'm going to, if I get the same example wrong a few times consecutively, its weight is going to go up, and it will force the weak hypothesis to do it, to classify it correctly, right? So this is basically what this says, and you can basically just think about it. This is the mathematical expression of it is very simple. All we did is we multiply this e to this expression m times. We started with 1 over m. So remember that that basically dt plus 1 is dt times this expression, e to the minus alpha t yh. I'm basically repeatedly multiplying by this expression for different t's, and I'm going to get this. And as we said, this is the final weight of the ith examples. Now, what is inside this parentheses? this is linear sum alpha t ht, which is really my final hypothesis. Okay? Right, remember that the final hypothesis is the weighted sum of the HTs. So that's going to be the weight of the final example. Okay, so the next step that I want to talk about is showing that the training error is really bounded not by what the final theorem says, but by the product of all the ZTs. And again, the reason I want to show it is mostly for you to think about what does it mean to be an error. So the first thing I want to say, again, this is something that you should be comfortable with. If the final hypothesis made a mistake, it's different than y, it means that y times f of x is negative. It means that e to the minus this is greater than 1. Okay? I'm going to use this. So now, what is the training error of the final hypothesis? So basically, in the final hypothesis, I forgot all the distribution. I'm just looking at my data, and I'm asking, what is the training error? So the training error is 1 over m times 1 summed over all the cases I made mistakes. Right? That's it. Right? So I'm basically counting here. I'm counting here all the examples on which I made a mistake. Now, given what I said here, I can replace this 1 by e to the minus y times f of the ith example, because it's greater than 1. So I'm replacing the 1 by something that is greater than it. And according to what I said before, this is just definition of training, as I said. This always holds. As I said, it's written above. And the last step is basically using step 1. Basically go to the previous slide and replace the definition of this ZT that I showed before, and you'll just see that that's what we get, e to the minus yi f of xi. How do I get from here to here? This is maybe the more interesting step that I wanted you to think about.
Because the weighted sum of all of them should be 1 always.
Right. So look at this sum here. This one is just a constant. Take it outside of the sum. So you have a constant, which is the product of all the ZTs, times the sum over all examples of the distribution of I. This has to be 1. It's a distribution. And therefore, we get this. So that's the next step. And the final step, again, there's some points that I want you to understand here. The final step is to show what is ZT, because together with 2 and 3, this will prove the theorem. So what is the ZT? We already expressed it this way. So ZT is a normalization factor. It means that if you sum, you have to sum the weight of all the examples in order to get ZT, because you divide it in order to get 1. You divide by ZT in order to get 1. So basically, by definition, ZT is this. It's the sum over all examples, the weight of the example, e to the minus alpha t yi ht. I'm going to split it here to 2 parts. Instead of summing over all I, I'm going to sum over all I on which I made mistakes, and sum over all examples on which I got right. Okay? Basically did nothing here. Right? Just summed over separately mistakes and no mistakes. Now, what is this? What is this expression? This is sum over all examples which I got wrong, dt of I, e to the alpha t. I can take the e to the alpha t outside the sum because it doesn't depend on I. What do you get here inside? Which is? But you know exactly what it is. So what is the sum of dt of I over all i's which I made a mistake on? It's the error. That's the error. That's exactly why I'm showing this slide. So what you should see here is this. The sum over all examples on which I made a mistake of dt of I is epsilon t. Okay, that's the definition of error. And on the other side here, what I have is, again, I'm taking e to the minus alpha t outside of the sum. So I have the sum of dti over all examples which I got right. So it's 1 minus the error, 1 minus epsilon t. Okay? So this is basically the definition of error, and you should be comfortable with this. So that's basically the key step. This is the definition of epsilon t, as we said. And the rest, if you go back to the definition of alpha t and substitute it, you're going to get this expression. So that's less important. Oh, the definition is here. So basically, the reason I show these slides is because it's writing, or all this three-step proof is because we are writing error in many, many different ways, or in several different ways, and it's important for you to understand what is the error and how to write it. So the rest is really just algebra, and it shows, as we said, that the error can be, the error of the final hypothesis will be as low as you want. Okay, so the key question is, why does it work? So why is it the case that we can get the error as low as we want? So your question was, I mean, the fact that that I have small epsilon on some distribution doesn't mean that I want to weigh this hypothesis high. This proof actually shows, yes, it does, because if you do this, you can get the error as low as possible. But what really makes AdaBoost work? Yeah?
The different distributions. So basically, you can weigh the examples. One hypothesis classifying as wrong. So you can make the next hypothesis ensure. So you can ensure that the next hypothesis will actually not make mistakes on the examples the first one made.
Okay, but good. But hidden in your comment is the fact that you rely on the weak hypothesis. So what does it mean that we rely on the weak hypothesis? What are we assuming on the weak hypothesis?
It's guaranteed amount.
It's less than half always. Right? So any distribution that you feed it to, you have a weak hypothesis for, which if you think about is a very, very strong assumption. Right? So you focus all your weight on this one example that gives you a problem. You are guaranteed that you can find a weak hypothesis that will get it right at some point, because its weight is going to be above a half with time. The distribution is going to put more and more weight on it. And there will be a hypothesis that gets it right. So really, the reason it works is that we made this weak learning hypothesis. It's called the weak learning hypothesis, but it's a very strong assumption. It says for any distribution, I can find a hypothesis that is doing better than a half on it. But with this, it works. And in fact, in life, okay, let's forget this for a second. In life, it works well in practice, even though it's completely clear that at least some of the weak hypotheses that you'll use are not really weak hypotheses. Right? So it's not true that you can do this for every distribution. Some of them will be wrong, but it still works. Okay, so as I said, boosting is very, very strong in terms of the ability to reduce epsilon. I put here a few slides which I will not get to because I'm running slow, about boosting the confidence, boosting the delta. But boosting the delta is less interesting because essentially what these slides show is that by repeating the algorithm many times, you will reduce, you will boost the confidence, so it's less interesting. I want to talk a little bit about ensemble methods in general. So boosting is one, that's what we talked about here. There are two other methods that are common. One of them is called bagging, the other one is called random forests. There are some similarities between them. There are some differences. So let's summarize. What did we see in boosting? We start by initializing all the training samples equally. We train a model. We compute the error of the model on the training set, and we increase the weight of the training cases that the model gets wrong. Basically, we do this typically hundreds or thousands of times, and we return the final model, which is the linear sum of this weighted by these alphas. So basically, the alphas are important here because they determine what's the importance we want to give to each weak learner. And as I said, turn out to be a very, very strong model. Now, I also said that there have been thousands of papers written about AdaBoost, and it's been analyzed to death from different perspectives. So people show that you can view it as a maximum margin algorithm. People show that it can, it has the various statistical properties. I'm not going to spend time talking about it, but really from your perspective, think about it. It's really a linear classifier, very similar to the one that you played with in homework 1. The difference is that there you basically learn the weights of the weak hypothesis, let's call them. It was small decision trees. You learn all the weights together with stochastic gradient descent. Here, we incrementally learn the weights as we introduce the hypothesis. This is a very, very, if you think about it, very strong way of doing it because the HIs are going to be determined as you go. You don't have a fixed set of HIs. You don't necessarily have a fixed set of HIs. Could be an infinite set of HIs that you add to a hypothesis as you go. Bagging. So bagging is another way to put together a lot of hypotheses. In this case, basically what you do, you generate the multiple hypotheses, the multiple versions, by taking what is called bootstrap replicates of the learning set, and you use them to generate a new learning set. So typically what you do is you sample the data with repetitions. For every sample of the data, you learn your classifier, and then you put them together. The key issue here is if you sample the data, you're going to get an approximation to the classifier that you care about. It's going to have a large variance, and eventually, if you sum a lot of this, you're going to reduce this variance. So you can think about it this way. You take 100 samples of the data. You train trees, for example. On each sample, you're going to get 100 trees. And then you average the prediction, and you get a new tree, a new classifier, which is a lot more expressive than your original. So in this case, I'm basically just averaging. I don't think about which of the weak hypotheses or the small trees is better. Uniform averaging. Random forest is an improved version of bagged trees. Typically, you need to use more trees than in bagging. And the idea here is that you don't only sample data, you also sample features. So you don't always use all the set of features that you have. So draw a sample of available attributes in each split. You train trees for each sample /attribute set. And again, you average the predictions. And again, this algorithm is known to be very, very good, stable, and doesn't have to be, the way I'm writing it here is you apply it over trees, you can apply it on whatever you want. You can apply it over linear models, you can apply it over neural networks, the same idea, and it's going to give you more stable hypothesis. Okay, so questions? Yeah.
How is AdaBoost different from its previous variants?
So AdaBoost doesn't need to know how good are the weak hypotheses. That's the key thing. The gammas, it doesn't matter what it is, it basically adapts to it, right? Because all the bounds are as a function of the gamma, which is the lower bound of all the gamma t's. That's one thing. The first algorithm was also a lot more sophisticated and harder to implement than this one. This one is very simple, right? All you do is you take your weak learners and you combine them. The previous one was iterative. For every round, you'll have to change the distribution 3 times, combine it, and then keep on going. So if you go to the original paper, you will see that the algorithm is quite complex.
So you said random forest is just a more stable version of bagging.
Yes.
So is there any situation where you use bagging over random forest?
The issue with random forest is that typically people use a lot more. They found that they need to use a lot more weak learners. So if you don't have time or space, bagging is going to do it. Now, remember that there is a difference also. So in random forest, you also sample on the feature space. In bagging, you typically don't. That's the key difference. Okay. So what have we done so far? So basically, we talked about classification with a lot of learning algorithms. And we basically talked about binary classification. So what I want to do in the next few minutes, and probably I'll finish it next time, is basically to say that's okay. I mean, what we've done with binary classification carries on to multi-class classification. Essentially, you can always take a multi-class classification and reduce it to a binary classification. Assume that you have a binary classification box. You can use it also to do multi-class classification. And there are multiple ways of doing it. And some of them are better than others, and we can understand what are the differences between them. So basically, all I'm saying here is that there are many tasks for which where the classification is more than binary, right? You can think about multi-class classification. When you have k-labels, you can think about multi-label classification, where not only you have k-labels, you want to label each example with a subset of those, because multiple labels are possible. You can think about document classification as an example, where one piece could be both a home page and a faculty page. You can think even about pieces of text, when something can be both a location, Madrid, or an organization, could be the football team. You can think about ranking as various, as the goal of your classification, where you have multiple labels and you basically want to rank them. You can think about hierarchical classification, where not only you have k labels, actually there is also some partial order between them. Maybe there's a tree of labels, that defines the taxonomy, and you want to know that there is a node that represents sport, and under sport, various kinds of sports. On the other hand, you have something that represents religion, and under religion, you have various aspects of religion, and so on. So in all these cases, it can be shown that really the binary models that we've learned could be good building blocks, and you can build on them more important, more expressive classifiers. I'm going to mostly talk about multi-class classification and basically show this. So what is the setting? We have a data set, M examples. In this case, the yi's are going to be taken from 1 to k rather than plus or minus 1. And the prediction is the same. and I'm going to assume that I'm going to output only a single label. So I'm calling this inference here because I already have some constraint on the output, right? I cannot just apply a threshold, just like we did before when we took the sign of the dot product, because applying a threshold may give me several y's that exceed the threshold. I'm going to take the max because I know that only one of them should be chosen. So now, how do we convert binary to multi-class? So there are multiple ways of doing it. I'm going to discuss 2 or 3 of these methods. We'll start with something that is called one versus all, and then move to all versus all. Okay, so what is one versus all? Or maybe let me ask a question. So I already gave you the name, so it gives you some hint. What would be the first thing you will do if you want to solve a multi-class problem and you have a box that knows how to solve binary problems?
Create many binary classifiers.
How?
Like class 1 or not, class 2 or not, class 3 or not.
Okay, so you have K classes, K labels, and you'll basically generate K binary problems. Is it label 1 or not, label 2 or not, and so on. What is the assumption that you're making when you're relying on this? So basically what you're assuming that 1 is separable from all the others, 2 is separable from all the others, where separable here is a function of the hypothesis space that you're using. Let's just think about it as linear, just for the sake of an example. So each class can be separated from all the rest using a binary classifier. So that's the assumption we're making. And with this assumption, we can decompose into K learning problems. How do we learn in this case? We have data. It's labeled with K examples. We basically define K learning problems. For each label L, we construct a binary classification where we say the positive examples are those that are labeled L. The negative examples are the rest. This is going to allow us to learn, as I said, I'm going to assume it's binary classifier that are represented as weight vector. So we're going to learn K weight vectors, W1 up to WK. And our decision is going to be argmax decision. So I'm going to compute Wi dot product with X, and I'm going to take argmax. Right? So basically, I'm essentially, given an example, I'm asking all the K learners that I learned, what do you think about this example? And I'm taking the one that shouts the loudest and say, okay, it's yours. Basically, that's the decision. So you can think about it this way. So I have, in this case, 3 colors, pretty distinguishable. I'm decomposing into this binary problem. So I'm distinguishing the black from the rest, the blue from the rest, the green from the rest. Now I have a problem. And this represents when we have problems in this kind of scheme, right? So I cannot distinguish the red from the rest using my linear classifier. So this is where the limitations of this approach are. So it's not always possible to learn. There's really no theoretical justification for one versus all, even though it's the most commonly used approach in multi-class classification. So you can see that sometimes it's not going to work. This is, by the way, sometimes a real problem, mostly in low-dimensional cases. In very high-dimensional cases, everything is separable anyhow, so you don't really see these kind of problems. But there are solutions to this problem that I may give you a hint about a little bit later. Okay, so a second scheme. what kind of scheme can solve this problem? Again, the assumption here is that each label was separable from all the other labels, from the union of all the other labels. What can I do if this doesn't hold? What would be another scheme? Yeah?
You need to separate all the labels from each other.
Which means?
So each label should be separable from each of the other labels individually.
Right. So you can see that this actually works here, right? So, of course, each label is separable from each of the other individually, otherwise the problem is ill-defined. Only that it's not separable from the union of all of them. So what I'm going to do is I'm going to look at pairs of labels and try to learn a model that deals with pairs of labels. And this is where what we call all versus all, or all pairs sometimes. The assumption is there is a separation between every pair of classes using a binary classifier in our hypothesis space. Again, I'm assuming that our hypothesis space here is a space of linear functions. So in this case, I'm looking at all pairs. So I'm looking at quadratic number of classifiers, right? So k choose 2, which is approximately k squared, independent binary classifiers. How do I learn here? So I learn k squared times, as opposed to k times before. In each case, I'm taking the ith examples as positive, the jth example as negative, and I'm learning for this pair. And then I'm doing it for all I and j's. Now, the decision here, so that's the learning. The decision here is going to be a lot more involved because now I have k-squared classifiers. You give me an example, what do I do? You see that there could be an issue here. I can run all the classifiers on it. What will happen? So if everything is clean and my classifiers are perfect, everything is fine because there's going to be only one classifier that wins in all these k-square models, right? So I can basically take the majority and everything is going to work. In real life, it's not going to happen this way. So I have to do something a little bit more sophisticated. And typically what people are doing is a tournament. You start just with, you take your examples, you take your classifiers, and you basically run them in pairs. It's going to, I don't have a picture of this. I do have a picture. So, as I said, one option is majority, and in perfect life, this is going to be okay. I'm basically going to count who wins. And the second option is majority, where I'm doing a competition here between red and blue, green and blue, and so on. And I'm moving up the winner and doing a competition there. So I'm starting with evaluating just half of the classifiers, and then quarter of the classifiers, and so on, until I get to the winner. Now, this, you can easily see that this could give you some cycles, and is not going to be perfect, but that's the approach. So I'm going to stop here and come back to revisit this next time, and just summarize what we know about multiclass. Final question? Okay, see you on Wednesday then. Fine.
Talk to you about that.
So how much did you use for that? The issue is it possible to date it? Why don't you send this to me?
Okay, sure.
And add comments what you told me, and we'll see what we can do.
Okay, sure. Thank you so much.
Okay, sure.
Towards the end, multi-class classification. Training cluster is derived from this.
Cluster is really an EM algorithm. We're going to talk about it in about. So K-means doesn't have labels. Here we have labels.
Oh, okay, that is unsupervised. It runs. So, the doubt is like, is deep learning a course in itself? Like, is it much more than what we are learning over here? Or?
Well, deep learning, there is a course on deep learning where people talk about more in more details than what we've covered here. There isn't a lot to teach in deep learning modular different architectures that people are using.
No, I'm graduating in this coming. So I just want to know like how far it is useful if I go and work in the industry. Should I take a deep learning course or is this?
You can try to take a deep learning course and see if it helps you. You are playing now with a problem set that involves deep learning. And this will, by itself, will give you some experience. Of course, you can do more things. Are you doing a project?
No, sir.
Okay, so you're in 419.
Oh, I'm in 519. I'm in 519, I'm doing a project, I'm sorry.
Oh, you are doing a project.
Yes, sir.
Are you doing a project that involves deep learning?
Yes, sir. Convolutional neural networks.
Okay, so this will already give you some experience. I think you should try, if you're interested in this, you should try to see how is the deep learning course. I think there is one next semester.
Yes, sir. Yes, sir.
So you can try and see.
It's worth it from an industry perspective, right?
Well, I wouldn't call it industry perspective, but it will probably, I don't remember who teaches it, but they will probably cover a lot more architecture, which, you know, you can cover yourself, but there's not a lot of theory or something like this. Basically, a lot of different models.
I see. Right.
But it will give you some exposure to what models people are using today. Okay.
Thank you, sir.
Sure.
Today, we're going to have a graduate student meeting today at 6 p.m. Is that for us or just for second year master's students? Yeah. You sent an email to us.
Oh, yeah. It's only for the undergrads, although not for, you don't need anything, no.
scientific learning